Today we're doing two topics at one time because honestly, they go together like a little handshake. So topics 1.9 and 1.10 are about we're zooming in a little bit on the undefined values that we learned about last class. So if we review just for a second, we know that rational functions are written with a fraction where there is a polynomial on top and there is a polynomial on the denominator. We learned in the last topic that values that the denominator equals 0, bless you, are going to be called undefined values for the rational function. So again, example 0 is our review, and we just did a quiz over this, so like we kind of remember. If we have this rational function, x minus 3, x minus 6, divided by x minus 6, x minus 2, we're going to try to find the zeros and the undefined values. Well, first things first, do you guys see that there are some similar terms in the numerator and denominator? Based on what we just learned from our quiz, what should we do first? Cross them out. Now, don't aggressively cross them out because we want to still see them. But those terms cancel out, meaning that is no longer a 0 because it's gone. It crosses out. So to answer the question, what are the zeros, we're actually only really highlighting that first little term in the numerator because the other one got canceled out. The interesting thing about this is, though, that our undefined terms are everything even if I did cancel it out. Numerator, if it cancels out, don't highlight it. Denominator, even if it cancels out, highlight it. To answer this question that asks for the zeros and the undefined values, we then look at the numerator to find the zeros. This function has a 0 at x equal to 3 only. But it will have undefined values I don't know why I struggled in my head to spell the word undefined, and I think I still misspelled it, so let's spell it that correctly. There we go. Undefined values. The undefined values will be x equal to 6 and positive 2. Okay, cool. Now this makes sense because if I had not remembered to not highlight the canceled out term, I would have accidentally listed a 6 on my zeros. But do you see how 6 is now on the list of both zeros and undefined terms? Can't be on both. The undefined values win, so we have to take it off of this list, which is why we cancel it out to begin with. Now, our job today is to think more about these undefined values and categorize them into two types of undefined values. The two types of undefined values we're going to have are holes in the graph and vertical asymptotes. So today, to follow my color scheme, we're going to use purple to talk about the holes in graphs, and we're going to keep using our orange to talk about these vertical asymptotes. Now, a hole is exactly what it kind of sounds like. If we were graphing this function, there would be a hole, a break, a tiny little value that we're not allowed to use, and it's broken. The graph is not continuous because it has that hole. This occurs when the multiplicity of a common denominator in the numerator is greater than or equal to the amount in the denominator. Basically what that means is when reducing common factors, sure did not hear the door, the factors in the denominator, will completely cancel out. So if you're canceling out terms, and it cancels completely out of the denominator, it is an undefined value that is specifically called a hole in the graph. On the other hand, a vertical asymptote occurs when the factor in the denominator has no common factor with the numerator or when the multiplicity in the denominator is greater than the numerator, which is a fancy way of saying when you're canceling out terms, the factor in the denominator does not completely cancel out. It may cancel a little bit, but it won't completely cancel out. If that's the case, then that undefined term gives us a vertical asymptote. So we have two types of undefined values now, a hole and a vertical asymptote. Let's see an example of what these might look like. On the side that's talking about the holes in the graph, we see on the f of x function that x minus 1 would cancel out of the top and bottom completely. Easy enough to know that that's a hole in the graph. But if you look at the second example, g of x, there are 3 x minus 1's on top and 2 x minus 1's on bottom. So 2 in the bottom and 2 in the top are going to cancel. How many are left over in the top? 1. But it completely canceled out of the denominator, yes? That is a hole in the graph. So if the multiplicity is bigger in the numerator, meaning things would cancel out and leave 1 in the numerator, it's a hole. If you'd like to see this written all the way out, this graph right here, this would be x minus 1 times x minus 1 times x minus 1 over 2 times x minus 1 times x minus 1. This is why we don't write them like this. We write them with exponents because, like, that's annoying. But if we canceled out common pairs, do you see that there's still 1 left in the numerator? But it completely cancels out of the denominator? That is a hole in the graph. If we switch to looking at the vertical asymptotes, for the f of x function, does anything cancel out at all? No, which would mean that x minus 1 is a term that would give us a vertical asymptote at 1. If we look at g of x, something does cancel out, correct? An x minus 1 from the top and one of the 2 x minus 1's in the denominator. But do you see how there's still stuff left there? If you have numbers left in the denominator, it's a vertical asymptote. It's like the vertical asymptote is stronger than the whole. So if it stays there, it's definitely a vertical asymptote. Now, what do these visually look like on a graph? I'll be honest, holes are really hard to see, especially if you're trying to graph on a graphing calculator and or Desmos. It doesn't show the cute little hole like my notes do. Do we see the hole right there? Yes. Ah, it's nice. We can see it. On a graphing software, it will not show up as a cute little empty hole. So you have to be knowledgeable enough to know that the equation will provide you with a hole to be able to find it. If you're scrolling through a table or scrolling through the graph, yeah, it will say undefined, but you won't just see a cute little hole there. You have to know that it's there. But a vertical asymptote, we 100% will see on a graph because it's going to look something like this. We have a huge break in our graph, creating a left branch and a right branch, or a left branch, middle branch, right branch, if there's more than one vertical asymptote. These are drawn typically, I know I made mine a solid line right here because I'm trying to make a point. Typically, we draw these as dashed lines, and you can kind of see that printed on your paper, it is a dashed line. So if you want to dash as you go down later on, maybe that'd be great, but for now, just to emphasize, we'll make it a solid line. Okay, both of these graphs, however, when we're talking about the undefined terms, we're not talking necessarily about end behavior, because these still would have a horizontal asymptote at 2, or a horizontal asymptote at 1. So we can continually think about that information we have and see that these graphs now may have both a vertical asymptote as well as the horizontal asymptote, but then there also might be a hole in the graph. Do we understand the difference between where a hole in the graph comes from as opposed to a vertical asymptote in the graph? They're both coming from the denominator, but a hole completely cancels out of the denominator, while a vertical asymptote stays in the denominator. Doesn't completely cancel out. Once we have these visual tools of looking at vertical asymptotes and looking at holes, we can start to expand our concept of limits by writing the limit statements at these vertical asymptotes and holes. So if we're looking at this graph right here on our paper, we're going to write limit statements that are approaching the hole. So notice that now instead of having our limit approach negative or positive infinity, what number am I approaching both times? 1. But what is the little extra stuff you see there? Like a little floaty negative and a little floaty positive. That's adding the phrasing from the left or from the right. Left side of your graph is where all the negative numbers are. Right side of your graph is where all the positive numbers are. So we would read this limit statement as the limit as x approaches 1 from the left of f of x is. This is the easiest answered on the graph. So what I'm going to do is I'm going to follow the graph along with my finger until I approach the number 1. Here's the number 1. Clearly, what is happening at the number 1? What is this called again? A whole. But we're not going to exactly to positive 1. We are approaching it. So as I'm approaching this number, what are my output values getting closer and closer to? 0. 0 would be down here. This is the output of 0. My output here is 4. And then I get closer and closer and closer and closer. What are my outputs getting closer to? 3. So the limit as we get close to -1 from the left side is the number 3. Because I'm pinching it in. I'm getting closer and closer from the left side. What if we go from the right side? So this next part here, when I change it to a plus side, it's saying the limit as x approaches 1 from the right of f of x is. This time you're reading the graph kind of backwards. You're going this way.
Going to 4.
As we get closer and closer and closer to this hole, what are my output values also getting closer and closer to? 3. Interesting. So it's as if we could put a little like Band-Aid on this graph right at the hole. It wouldn't matter because one side goes to 3, the other side goes to 3. That has a limit as we're getting closer on each side. So when I'm doing these for myself and I'm like, put my iPad down so I could show you, I'm literally like pinching it with my fingers. So I know my left hand's going to show me as I go to from the left side, and my right side, if I point it backwards, is going to be the limit as we go from the right. So that's the good concept to think from the left, from the right, like you're pinching it. Okay? Now we can do the same concept for vertical asymptotes. And again, this one, we're still approaching 1 from the left or approaching 1 from the right, but we're getting closer to a vertical asymptote this time. So if I'm going from the left and I'm pinching it in towards the vertical asymptote, where are my output values getting closer and closer to? Negative infinity. So these vertical asymptotes are going to have limits from a number to one of the infinities instead of from a number to a number. What happens if I'm coming in on the other side? And this time I'm getting closer to this vertical asymptote from the right. What's happening to my graph? It goes up, so my limit is positive infinity. Again, the concept of pinching it makes sense because we're pinching it, getting closer and closer to the vertical asymptote. My fingers are going opposite directions. One is going down, one is going up. Writing these limits is a little bit challenging because you're like, there's so many numbers floating around different places. I know. What I want you to think about is that a limit from a number to a number gives you a whole. A limit from a number to one of the infinities will give you a vertical asymptote. A number, if this is one of the infinities, I'm talking about end behavior. That's a Bobo, Bot, and Betsy question. But when there's numbers here, we're talking about a whole or a vertical asymptote for the most part. Now, this last little box up here is not going to be important just yet until we go to the back, but it says to find a limit at a whole analytically, you're going to cancel out the factors and have a reduced function and then plug in the number for the whole. Becomes an evaluating question. But if we're trying to find the limit analytically for a vertical asymptote, we're going to have to complete a sign chart, everybody's favorite thing, at a near number to that limit that we're approaching. And I'll show you examples of that on the back, but I just wanted it all on the front, so this is like a nice little reference page for you about wholes and vertical asymptotes. Let's flip this thing over and try some example problems. Remember, this front is a reference page now, so you can flip back and forth to it each time. On example 1, for each of the functions below, we're going to determine the x values of any wholes or vertical asymptotes. So I'm not talking about the zeros necessarily anymore. We're going to be focusing on those denominators. But before we do anything, we should cancel out common terms. Are there any common terms here? X plus 3. Okay, cancel. Cool. I know that the undefined values still come from here, which is where I'm going to find my wholes and my vertical asymptotes. If one of these two terms completely canceled out of the denominator, it is a whole. Did anything completely cancel out of the denominator? Yeah, which means there's going to be a whole at x equal to -3, because that one completely canceled out of the denominator. There's going to be a vertical asymptote at x equal to 5, because that factor did not completely cancel out of the denominator? Yes? Okay. Now this next one, are there any things that can cancel out? Yes, tell me about them. Both of them can cancel, right? So I'll stop by canceling the x plus 1s. There's only one in the top, which means I can only cancel one in the bottom out of the two that are there. The x minus 2, there's one in the bottom, which means I can cancel out one in the top. Either way, all of our undefined values come from this denominator. Did anything that I've highlighted orange get completely canceled out of the denominator? One of them did. There's going to be a hole at x equal to 2 because x minus 1 was completely canceled out. We'll have a vertical asymptote at x equal to -1 because x plus 1 I didn't completely cancel out. Part of it canceled, but not all of it. All right, let's look at this last example. G of x equal to 1 over x cubed plus 4x. Ooh, this one's not in factored form. So it's good practice to always write them in factored form first so we can see if anything were to cancel. So the only way I can factor that denominator is by taking out a GCF. Both of those terms have an x in common, so I'm going to factor out that x. Once it's in this factored form, which this is as factored as we can get it, are there any things that are going to cancel out top and bottom? No, because there's only a 1 in the numerator. So, okay, we have these two things. Since nothing canceled, we know that there are no holes in this graph. Check. Oh, you know what? Y'all gotta stop me when I'm being crazy. This should just be 4x. I mean, sorry, 4. Wow, I just did it again. Do y'all know why it should be just 4? The x was supposed to factor out. I don't know what I was doing. Okay, so let's find the vertical asymptotes. From this factor, it's probably pretty simple. What's the vertical asymptote that comes from just this plain x right here? What is the vertical asymptote equation that comes from just this plain x right here? If it was 1, it would say x minus 1. Is there a plus or minus any number next to that x? So it's 0. It's 0. There's no plus or minus any number. So the vertical asymptote for that pair would be 0. Now the question is, that second factor is x squared plus 4. And what we're really doing when we're finding these vertical asymptotes is we're taking each factor, setting it equal to 0, and solving for x. We've just been able to take a bunch of shortcuts because the solving for x part has been really easy. If we subtract 4 from both sides to start solving for x, how do I get that x squared to just be a single x? Square root it. Ooh, what? I'm square rooting a negative number? Can you square root a negative number?
No, you can put I.
We'd have to use I. And can you plot an I on a regular looking coordinate grid? No. So when if you're solving these things and you end up with some sort of imaginary number, you need to remind yourselves that there are no vertical asymptotes or holes at imaginary numbers. So in fact, that is our only vertical asymptote here. It is just at 0 because we couldn't solve for another real number where the denominator would be equal to 0. Okay, let's kick it up a notch. And we're going to write our limit statements like we did on the front page, but I'm not giving you a graph this time. We're going to write a left and right side limit statement as x approaches 2. That's our goal here, is for x to approach 2 for each of the following functions. Now, if I were to immediately plug the number 2 into this function, what would happen? If I plug the number 2 in right here, what would happen? Yeah, denominator would be 0, right? Can denominators be 0? No, that's how we got in this mess to begin with. So we have to decide when we do this here or here, because both of them would give me 0, whether we're going to end up with a vertical asymptote or a hole at that value 2. So my question for you is, does anything cancel out of this denominator? No. So is there going to be a vertical asymptote or hole? Vertical asymptote. If we're having a vertical asymptote at 2, which we are, the way that we find the limit statements, and this is from the front of your page, it says we're going to make a sign chart with close numbers. So let's figure out what that means. If we had our coordinate grid, number line, and here's the number 2. We know we can't use it. I just need to know something that's occurring relatively close to the number 2. What's a number that's very close to the number 2? Get closer. 1, get closer. 1.9 is fabulous. On this number line, 1.9 would be like right there, yeah? What's another number that's near it, like just barely bigger than 2? 2.1 is fabulous. Those numbers are near the number we care about for this problem. We can't use 10 because we're not trying to determine if things are above or below. We're trying to figure out what happens as we get close. So we need to choose numbers that are close on either side. So just a little bit below and just a little bit above, so we can really see what's happening as we get close to 2. That's what the idea of a limit is, as we get close to that. But that's what we're going to plug into our sign chart like we did in the last class. So if we let x equal to 1.9, 1.9 minus 1 would be a positive number. 1.9 plus 3 would be a positive number. 1.9 minus 2 would be a negative number. Positive times positive divided by negative, what would that be? A negative number. Let's do the same thing, but let's use 2.1. If you're like, what is Ms. Quigley plugging these numbers into? The original equation printed on our paper. 2.1 minus 1 is a positive number. 2.1 plus 3, positive number. 2.1 minus 2 gives me 0.1. That's a positive number. That section is positive. Since barely on the left side, the 1.9 side is negative, that means that the limit as x approaches 2 from the left side, 1.9, for this function f of x, since we got negative, is going to be negative infinity. Since on the very, very right side, 2.1, when we plugged in 2.1, we're pretty close to 2, but we're on the right side of 2. And we got a plus sign. It'd be positive infinity. So to write these limit statements, we create a sign chart with close numbers. Just go barely below it and barely above it, so we know what's happening as we get close. Yes? Go ahead. For this second function, if we start at the beginning where we always start by looking to see if things will cancel out, Do you see that the x minus 2 term will cancel out of the top and bottom? Which means the number 2 represents a whole. This time there's a whole at x equal to 2. Our theory changes on how we write the limit statement when it's a whole. The front of our paper says that we're going to cancel factors and plug in. Good luck today. This one is actually really pretty simple because you've already canceled out the factor. You see how g of x, you crossed out the x minus 2 on top and bottom? What you would have left is just x plus 4 and x minus 3. That's the reduced version of your rational function. You see what I did? All I'm going to do now with this reduced version is I'm going to plug in 2. 2 plus 4 on top and 2 minus 3 on bottom. 2 plus 4 is 6. 2 minus 3 is negative 1. I get negative 6. Since that's what I would get, as if the whole was not even there, I canceled it out. That means that both the left and right limit statements, the limit as x approaches 2 from the left of g of x, will be negative 6, and the limit as x approaches 2 from the right side of g of x will also be equal to negative 6. So whatever number you get when you cancel out the factors and plug in the number, that's what your limit statements will be equal to as you get closer and closer to that whole. I know that these two concepts are like wildly different. You're like, wow, well, just one example? Yes. Sign charts we've done before. All you're doing is it's a sign chart from a number close by, or you're just plugging in a value. We can find these limit statements visually really easy looking at a graph, and now we can do them analytically. But let's focus in on these limit statements because they're new. The way that they're written is new. I want us to recognize whether a limit statement is talking about a whole or talking about a vertical asymptote. So if you'll notice, we have 4 limit statements here. These two are both approaching 3, one from the left side and one from the right side. But as we approach 3 from the left and the right, it's equal to 5. Does that mean that there is a whole or a vertical asymptote at 3? A whole at 3, because the number, if it's a limit approaching a number equal to a number, that's going to show us a whole. Now, if we're approaching a number, like the left side going to 1 and the right side going to 1, or 1 from the left, 1 from the right is the correct way to say that, and these are going off to one of the infinities, is that a vertical asymptote or a whole? Vertical asymptote at 1. Now, this actual question, example 3, wants us to write an equation where this would happen. So what we're going to do is we're going to take the concept of what a whole should do and a concept of what a vertical asymptote should do and put it together. Meaning, if we were writing a function f of x and we need it to have a whole at 3, that means that we would put x minus 3 on the top and x minus 3 on the bottom. Why would I do that? So it can cancel out. Because it's a whole. It has to happen on both the top and the bottom. Since I know there's a vertical asymptote at 1, that also means that on the bottom, I'm going to have x minus 1. Should I put 1 on top? No, because we need it to stay in the bottom when it cancels out. This is an appropriate answer to this question because we read that there is going to be a whole at 3 and a vertical asymptote at 1 and made our equation do that. Can you guys try letter B? I want you to write that equation for me based on the properties you see written there. The top two limit statements are limits as x approaching 2 from the left side and the right side, and they're equal to 4. Does that mean, well, what does that mean is happening at -2? There's a hole. Nice. So we have a hole at x equal to -2. And since the other two are going off to some of the infinities, we're going to have a vertical asymptote at x equal to -1. So if that's the case, when we go to write our equation for f of x, we know that holes have to cancel out on the top and bottom. So there should be an x plus 2 on the top and an x plus 2 on the bottom. Then there should be an x plus 1 on the bottom. Now here's a bit of extra information. Do you notice how in question A, one of the limits was positive infinity, the other one was negative? And do you see how in this one, both of the limits go to positive infinity? That's called togetherness about an asymptote, and we're going to dive more into that in a couple lessons. And I'll get into more of that later, but really that means that the multiplicity of this vertical asymptote has to be squared. If they're going the same direction, there's an even multiplicity. So these are going the same direction. I have to make this have an even multiplicity. Since these were going opposite directions, we can leave the multiplicity as 1. It's an odd number. And again, I'll dive more into that in a couple of lessons when we start to really graph these rational functions by hand. Today, we're just going to sketch rational functions by hand. We'll get more into the graphing later. So example 4 wants me to sketch a picture of a rational function, which means it doesn't have to be super duper accurate. When I say graph, I want accuracy. When I say sketch, get close. We're going to sketch a picture of a rational function that has these properties. We know that when we graph this, we want our function to have a hole at 1, a horizontal asymptote at 0, and then I'm given the words, as x approaches 4 from the left, f of x increases without bound, and as x approaches 4 from the right, f of x decreases without bound. Increases without bound, remember, means positive infinity, and decreases without bound means negative infinity. So what is in fact happening at 4? Yeah, if one of them's going up and one of them's going down, what's in the middle of them? It's one of our vocabulary words for the day. A vertical asymptote. If you see this, that means the limit statements are going opposite directions. That's our vertical asymptotes. We also know that there needs to be a hole at x equal to 1. And since we've been using yellow for our horizontal asymptotes, we'll graph that as well. This is just a sketch. We're going to get it as close as possible. So we draw our x-axis and our y-axis. We know we have an important point at 1. So here's 1. And we know we have an important point at 4, so something cool is happening at 4. I need to make sure I at least see those numbers on here. I know that there's going to be a hole at 1. I know that there needs to be a horizontal asymptote at 0, so I'm going to go ahead and highlight 0, which is my x-axis, to say you cannot cross this line at the end of the graph. You can cross it in the middle, potentially. You cannot cross it at the end. I also know that there is a vertical asymptote at 4. I know I left off purple for the hole. We're going to get there. It's one of the last things we draw in there just because it's hard to graph first. I also know that as x approaches 4 from the left side, which means on the left side of this vertical asymptote, should my graph be going up or down? Up. So what we're going to do is we're going to leave ourselves a little up arrow because on the left side it should be going up. What should be happening on the right side? Down. So I'm going to leave myself a little down arrow. Our job is to play connect the dots. But remember, at the ends, you cannot cross the yellow line. So starting at the vertical asymptote and working my way to the left, if I were to do this, I'd have to come by and then whoop, get close to but never touch that horizontal asymptote. What's going to happen at 1? There's a hole. So I make sure I leave an actual hole there, and then I can keep going. Again, connecting the dots, hardest part of graphing a rational function. If I start on this side, I'm going to grab that line that's going down, but I'm going to come up and then get close to the end behavior and then swing outwards because I cannot cross that horizontal asymptote at the end of my graph. That's a sketch of this rational function. Graphing rational functions is like advanced connect the dots. There's so many rules you have to abide by. Can I do one more with you? Okay. This one, g of x. Oh, there's a whole bunch of typos here. Those should all say g of x's. Let's fix. G. How about g? How about g? LOL. G of x has a hole 2 places. It has a hole at -2 and it has a hole at 3. So we have to make sure to put a hole in our line, our curve there. The horizontal asymptote this time would be at 1. And it says, as x approaches -1 from the left, g of x decreases without bound. And as x approaches -1 from the right, g of x increases without bound. So since that's where I'm increasing or decreasing without bound, that's going to be my, what is it called again? Vertical asymptote. Nice. So let's graph what we can. Here's my x-axis. That's crooked. You get it. Here's my y-axis. Important points I need this time are a hole at -2 and at 3. Horizontal asymptote at y equal to 1. So here's 1 on my y-axis. I also know something interesting happens at -1. So I'm going to go ahead and label that point. So to me, the sketch, I'm labeling the points where something happens so that I know to put stuff there. Here's what we know is there. We know that there is a vertical asymptote at -1, so I can go ahead and draw that dashed line in. There's my boundary line. Cannot cross that line. You can get close to it, but you cannot cross it. I also know that I have end behavior that my graph should get close to, but never cross 1 on the outsides of the graph. You might potentially cross it in the middle, but that's end behavior. Rereading my limit statements, it says as x approaches -1 from the left, so that's this side, g of x decreases without bound. So where should my arrow go, top or bottom? Bottom. So I'm going to put I'll connect the dots later type of arrow down at the bottom. And on the right side, where should I put the arrow? Up. Increases without bound going towards positive infinity. Okay, cool. You have to go from the arrows we just put on the vertical asymptotes towards the horizontal asymptote for the end behavior and then flatten out. So if I'm starting here, am I going to do this? No, because I just crossed the horizontal asymptote, didn't I? I'm gonna whoop. Okay, when I start to do that, that's great. But what do I have to remember to do at -2? Put a hole. Whoop. We don't have information on what the limit at the hole is, so we can put it wherever we want for now. And then I'm going to do the same thing on the other side. But remember, we cannot cross that horizontal asymptote. So this is going to be kind of flat, kind of quick. But I remember at 3, put a hole right there. And then I can keep going. That's a sketch of a rational function. It's like advanced connect the dots. And it's just going to keep getting advanced as I give you more things to be able to graph these rational functions accurately.